Hello, my name is Kevin, and this is Lab Group 3B on Tuesday mornings. So for Lab 7 here, we eventually wanted to measure the MTF for the test lens, but we started out by measuring the diffraction from a single pinhole aperture. In order to do that, like in previous labs, we have Heaney laser aligned along the rail, then through a microscope and a spatial filter, then through a collimating lens, which creates a collimated beam large enough to fill the entire aperture when it's full at its entirety. The beam is then deviated 90 degrees onto another rail. Then for part B of the lab, we have it going through the smallest aperture size on here and then aligned through a microscope onto a test screen. So according to our estimated measurements of the aperture size, we estimated that it was around 1 millimeter in radius. And according to this formula here, in order to get to the first Fresnel zone, it needs to be around 1580 millimeters distance between the aperture and the microscope. And we actually measured it to be 1353 millimeters, which means that our aperture size is actually 0.925 millimeters in radius. Then as we move, can you help me here? The microscope further along the rail, along with the test screen, we can move through different Fresnel zones. So the center spot where it's dark right now is actually going to get lighter and darker in different areas as we move through different Fresnel zones. So in the next part of the lab, we inserted a test lens with a focal length of 1,000 millimeters, and then immediately afterwards, an aperture stop as close as we could get to the lens. And then what we did is adjusted the microscope and found points on the image screen where the center was dark, which represents Fresnel zones of plus and minus 2, which is plus and minus 1 wave of defocus, and we measured the distance between those 2 points and measured that as a function of the aperture size. And the results we got are here. And as you can see, as the aperture size increases, the distance between the Fresnel zones decreases.
Greg, for part D, we were told to create a diffraction limited system, and we were basically told that we wanted an airy disc size of 200 microns so that we could scan across it in 20 increments of 10 microns. So we kind of reverse engineered it using this equation here, which is the equation for airy disc size. Basically kind of worked our way down here with a little fancy algebra. F being the focal length of our test lens, which is 1 meter. So we calculated the desired aperture size, D, capital D, to be about 7.7 millimeters. We used that to calculate our F number, and then used that to calculate our cutoff frequency, which is 11 about line pairs per millimeter. The inverse of that is the slit width, which comes out to about 85 microns.
And I'm continuing with Greg. After we measure the size, the optimum size for our aperture, we insert the aperture in and we start to sampling the best focus, plus one and minus one wave defocus. So this one is the size of the aperture. The slit is around 8 micron, and we will scan across it. And this one is what you're going to see after we scan across it. The first one, this one is the best focus. This one is the minus one, and this one is the plus one. They supposed to be on top each other, but for some reasons we didn't see in the top each other. And plus, we see diffractions from the slit when the light hit the detector as well. So that may cause the uncertainty in the measurement when we take the measurement.